Hello everyone, I'm Jinhan Yang, and today I'll present you a ring referral scheme, which is a natural extension to ring signature. For the clarity of presentation, we'll only present the multi-message ring referral scheme considering multi-message BBS signature. First, we'll talk about some privacy challenges in credential presentation. Then I'll briefly talk about some background primitives for a better understanding. And then we'll talk about what is actually the ring referral scheme and how it works. In protocol design part, we'll show its building blocks and key contributions. Later, we'll discuss its security and evaluation results, and some future works related to this scheme, and finally some key takeaways from this work. Imagine when you want to prove you are over 18, you may need to present your driver's license. But today's identity system often forces you to show the entire credential, like a digital license issued by a driver's authority, along with a proof showing your date of birth within a valid range. There are actually many authorized issuers of credentials, like each province in China issues driver's license. Presenting the identity of the issuer may leak sensitive personal information, like presenting the issuing address of your driver's license may leak your personal location. This leakage can be a very serious privacy problem. So how can we verify the credentials' validity without exposing the issuer or any extra personal information? This problem will be addressed by this ring referral scheme. A ring referral scheme allows the user to publicly prove her knowledge of a valid signature for her private messages that are signed by one authorized issuer in a ring, without reviewing this issuer. Let's break down the key concept in this scheme. First, what is a credential? It's a set of attributes that uniquely identifies who you are, like your driver's license, a membership card, academic diploma, or passport. Ring signature. A traditional ring signature is a signer proves that a message was signed by someone in a particular set of public keys without revealing which member signed it. This provides issuer anonymity. Talking about issuer anonymity, this is a property that when you want to show a credential, the verifier cannot tell which issuer signed it. Why is this important? Because reviewing the issuer can leak information about you. As mentioned before, even knowing the province that issued your driver's license can reveal your likely residence. For decentralized identity, it means users hold credentials issued by various authorities rather than a single centralized provider. In decentralized identity, you might have multiple trusted issuers, like different universities issued diplomas, different companies issued your working IDs. Last one, for user anonymity. We often want to unlink a signed message and its signature, even if there is a collusion among the issuers and a verifier to track a user. For example, proving you are a student from Hong Kong to get a student discount without revealing your university's name and your name. Ring signatures already hide the signer identity. Meanwhile, our ring referral scheme will also ensure the user isn't linkable through showing of the credential. To be more specific, again, what is ring signature? It's a type of digital signature in which a group of possible signers are fused together to produce a distinctive signature that authorizes a transaction or private messages. It's like a sealed transaction signed by either Alice, Bob, or Carol. The signature itself proves one of them signed, but you cannot tell who are the real signer. To a third party, all of the inputs appear equally likely to be the output being spent in the transaction. But there is also some problems in ring signature. Traditional ring signature hides the signer, but requires the signer herself to generate the proof. The person proves the signature's validity is actually the one who signed the message using their own secret key. This doesn't directly apply to typical credential scenarios where one party issues and another approves, and ring signature could not simultaneously achieve message hiding, threshold scheme, and smaller proof size. So we have ring referral scheme. Is a new cryptographic scheme which is also an extension of ring signature, where a user can prove I have a valid credential signed by one of these trusted issuers without revealing which issuer signed it. This scheme introduced stronger user anonymity, meaning that even if someone later gets access to the issuer's records, they cannot still link a presenting proof to a specific user. This is achieved by hiding the signed messages during the proof so that no other private information leaks. Think of referral marketing again. A bookstore offers a discount if you have a referral from any university in Hong Kong. Suppose you have a student ID from the Chinese University of Hong Kong. To prove its eligibility, you may show your student ID directly. Now with strong issuer anonymity, you can prove I have a valid student ID from some recognized university without showing the specific university's name. The bookstore just see a valid proof and gives you the discount without knowing which university you came from. Then let's talk about the key contributions about this scheme. Any public members can verify a ring referral scheme without the interaction with the user, and anyone can construct or update a ring without the need for approval by a verifier. We use standard BBI signature without letting the issuers know if their signatures are used in a ring referral. We also support a transparent setup to eliminate any third party in a decentralized setting. Our scheme can achieve message hiding, user hiding, and use a recursive compression technique, DORI, to achieve log size proof, and we also support upgrading it to the threshold scheme. How ring referral scheme works. First, a user obtains a credential from one authorized issuer in a set of issuers. Later, she proves to a verifier that she holds a valid issuer-signed credential, without revealing which issuer signed it. The verifier checks the proof against the public keys of all trusted issuers in the chosen ring, and accepts it if it validates. For building blocks, we present a ring referral scheme based on standard BBI signature on multi-messages. We use DORI to achieve log size proof size, plus homomorphic commitments like Peterson AFGHO and binary selector vector to hide the real issuer in a ring. What is BBI signature? Our ring referral scheme relies on message hiding signature scheme, in which the signed message's M is not revealed during the verification, except a commitment of this M. The validity of a BBI signature sigma 0, sigma 1 on messages M with respect to public key PK can be checked by this bilinear pairing equation, where G1, G2, vector G2, vector H are all generators from the setup. In our scheme, the verifier outsources the computation of E vector H, a vector G2 exponent to vector M to the prover. To check the consistency of the same messages M are used in both equation and the commitment, we use DORI. And what is DORI? DORI is a compressed zero-knowledge arguments of knowledge protocol with log verification efficiency and proof size based on a recursion for checking the following inner product relations in these pairing settings, where D0, D1, D2 belongs to group T, and random generators gamma belongs to group 1, lambda belongs to group 2 are the given input. Q is belong to the format of G1 and G2. They are all generators. And omega belongs to group 1 and theta belongs to group 2. and we have random values R0, R1, R2. They are all private witness. We use two commitment schemes, Peterson and AFGHO commitment. Both are homomorphic commitment schemes that support perfect hiding and computational binding. The overview of ring referral scheme, which each issuer first uses his public key and private key sign on user's messages, and send its BBS signatures to the user. The user knows a public key PK for specific issuer, assign the multi-messages vector M, and corresponding signature sigma. She will first commit the signature as well as public keys and messages. She will use these commitments to prove that PK M sigma is a valid multi-message BBS signature tuple. Given the commitment of the public key, the prover should also prove that the commitment of the public key is one of the ring. Then the user will output the proof to the verifier. Let's first see an example on single message. First, we generate the public parameters. The issuers will use them to generate their own secret key and public key, and use them to construct an element big R, and sign on the messages M. Once the user receives the signatures and check its validity by this equation, E sigma 0, G2 to the exponent sigma 1 multiply this public key PK and check if it is equal to E G1 multiply vector H exponent to vector M, G2. And how this equation works? It follows the so-called BBS check. If the signature is generated correctly, both left-hand side and right-hand side will be equal. Now we will outline the basic idea of a compressed message hiding multi-message BBS signature scheme as follows. First, the sender produces a valid BBS signatures, sigma 1, sigma 0 on messages vector M, and has the messages vector M in a Peterson commitment scheme defined as CMM, where it equal to vector gamma exponent to vector M multiply P1 exponent to Rm, where P1 is our generator. Rather than standard BBS signature verification, the verifier outsources the task of computing D0, which D0 equals to E vector H exponent to vector M, G2 multiply Q exponent to RD. To relate CMM and D0, we pre-compute D1 and use Dory to check the following, where gamma, lambda are known generators, and vector H in blue color, and G2 vector G2 exponent to vector M in red color are our witness. Then the verifier gives a public coin challenge theta to the sender. The sender will provide quotient small r and big R to the verifier. Finally, the verification of a BBS signature with respect to CMM and the public key PK can be checked through this pairing equation, which is also based on BBS check. The detailed compressed message hiding multi-message BBS signature scheme is presented in this figure, which you can see for multi-message. We commit our messages along with a Dory proof as output to the verifier. For proof knowledge of multi-message BBS, the prover knows a public key PK, assigned multi-message vector M, and the corresponding signature sigma 0, sigma 1. The user will first commit public key PK and signatures sigma 0, sigma 1 by AFGHO commitment scheme, and then commit vector messages vector M by Peterson commitment schemes. Then the prover will also provide 3 additional commitments Z1 and Z2 and D0 and send them together to the verifier, which enables the checking of multi-message BBS signature sigma. The key point to achieve efficient verification is that the verifier can first compute D2 herself, where D2 is the commitment of the vector m, G2. And then the verifier can use an m+1 dimensional recursive Dory argument to check the well-formedness of D0 using Dory's scalar product check, where gamma, lambda are known vector generators, and vector h, 1, G2, exponent to m Rm are our witness in this scheme. Finally, the verification of a multi-message BBS signature with respect to CMM, Z2, and Z1 can be checked by this pairing equation, which is also an extension to BBS checking. We multiply Z1 and Z2 and check if it equals to E G1, G2 multiply D0 multiply Q exponent to quotient R, where quotient R equals to RZ1 plus RZ2 minus RD is also provided by the user. And if our Z1 and Z2 are well formed, Q exponent to quotient R will be cancelled out on the both sides. And on the right hand side, D0 only have E vector H exponent to vector M, G2 now. And we can combine together with E G1, G2. And we will get a new equation which is exactly the BBS checking equation again.
Given the commitment of the public key PK, the prover should prove that the committed PK is one of the ring. We outline the basic idea of a proof of knowledge protocol. First, in the setup, we hash each issuer's public key PK, and then the user defines a selector vector, where the actual sender is the 1, other issuers remains 0, and the user commits vector B to an AFGHO commitment. Then the prover needs to prove that the vector B is indeed a unit vector committed in the commitment number 1 via Dory. This proves the knowledge of the index I star, which is the actual sender, belongs to the ring, and it remains to prove the knowledge of the public key PK I star. The user also commits the HI star, which is the hash value of the actual sender, as the commitment number 2. And finally, the verifier can check the validity of the commitment number 1 through commitment of public key multiply commitment number 2 multiply Q exponent to quotient R, which is also provided by the user. Since only the actual sender is 1 and others are 0 in this vector B, then on the left-hand side, if we multiply the G vector 1, key together, we will only have E G1, PKI multiply G2 exponent to HI exponent to BI, which others become 1 for this multiplication. If our hash value for the real sender is generated correctly, then this equation will work. Ring referral scheme follows the property of public verifiability. Anyone can check the knowledge of a committed value in a Peterson or AFGHO commitment through an interactive method. Like we have a Peterson commitment Px, a P exponent to x multiply Q exponent to R, and we want to prove the knowledge of x and R. We first generate new quotient x and quotient R, and generate the new commitment quotient Cm to the verifier. And then verifier can generate a random challenge alpha to us. and we will compute z, which is alpha multiply x plus quotient x, and rz, which is alpha multiply r plus quotient r, and send them together to the verifier for the check. And also, anyone can check if a committed vector B is a unit basis vector satisfying the following equations, where the first equation means that the sum of all the components of vector B equals to 1, and the second equation means vector B is a one-hot vector, which means exactly one element is 1, and the rest are 0 in this vector B. And we can extend these two equations to the following bilinear pairing equations. And for efficient calculation, we can use Dory. Each of the set of inner product relations can be checked by a Dory argument like the following. The first Dory argument will check the witness vector G1 exponent to vector B in blue color, comma vector G2 in red color. The second Dory argument will check the witness vector gamma exponent to vector B in blue color, and vector key exponent to vector B in red color. And for the last Dory argument, we'll check the vector G1 in blue color, and vector key exponent to vector B in red color. If all the Dory arguments pass, then vector B is a unit vector, which means there is exactly one sender signing the messages for us. The security of a referral scheme achieves unforgeability, as no attacker can fake a valid credential or proof without an authorized issuer's real signature, which means if an issuer doesn't actually send a message, a user cannot convince the verifier otherwise. And it also keeps the issuer anonymity as a ring signature. The verifier cannot tell which issuer in the ring actually issued the credential or sent the messages. Meanwhile, it realizes strong user anonymity against collusion among the issuers and the verifier, which means the credential holder also remains anonymous even across multiple presentations. The attacker cannot link a given proof to a specific user or credential in our scheme. For the scheme performance, the authors built this scheme against a baseline of the 2021 Issuer Hiding Credential Scheme paper, ECA 21. Ring referral schemes' proof sizes are much smaller than ECA 21. Verification is also faster. For example, verifying a credential with number m attributes requires only about big O log m pairing operations in ring referral schemes, but we need to have big O m in ECA 21 scheme. Moving on to the future works, this scheme relies on pairing-based cryptography, which could be broken by quantum computers in the future. So the authors mentioned about exploring lattice-based versions of ring referral scheme. A lattice-based construction could ensure security against quantum attacks. Also, the authors mentioned about a real-world evaluation of ring referral schemes on decentralized identity system that will be pursued in the future. A very obvious problem of this ring referral scheme is that when an issuer sends a user's attributes or messages, the issuer will know what is sent. So a possible enhancement is blind signature, so the issuer doesn't learn the user's actual information. This would mean the issuer provides a signature without seeing the plaintext attributes or messages. The issuer now cannot track the user's credential details either. Some takeaways for you. In this presentation, we presented an efficient cryptographic primitive called ring referral scheme, by which a user can publicly prove her knowledge of a valid signature for a private message that is signed by one of authorized issuers. Our referral scheme supports many distinguished features by upgrading the traditional ring signature with third-party signing. It guarantees issuer and strong user anonymity with lock-size verifiability and transparent setup. Ring referral scheme offers public verifiability with strong anonymity for both issuers and users simultaneously. It also supports complex scenarios like multi-message credentials and threshold-based scheme. In particular, it can be applied to certificate hiding decentralized identity system, privacy-enhancing federated authentication, anonymous endorsement, and privacy-preserving referral marketing. Thank you for your listening. If you have any question, please leave your comment below the video. Thank you.